Welcome back to Backspace Academy. So in this lesson we're going to run through a virtual private cloud. We'll talk about regions, availability zones, and how a VPC fits within those. We'll also look at IP subnet addressing and site notation. If you don't already know that, if you do know that, then probably skip over that. We'll look at the ways of connecting to a VPC, and we'll look at routing of traffic inside a VPC, and we'll also look at public and private subnetting, so dividing up our VPC into subnets that have private and public subnets. And we look at the techniques for VPC security, in particular security groups and network access control lists. So the AWS global infrastructure, 11 regions. You would choose a region based on minimum latency. So if you're in Australia, you would select Sydney, obviously, but you also might want to select a region to minimize costs because, for example, Sydney is significantly more expensive in resources than US North Virginia. So you might want to use that region rather than Australia if you're in Australia. Or you might want to use a different region to host your site depending on regulatory requirements of that region. So within regions we have 28 availability zones, so that varies, but they are insulated from failures in other availability zones. So within a region we have these insulated zones that can be used for providing of durability and redundancy of your infrastructure. So you can see there in North Virginia there are 5 availability zones, whereas in Singapore there's only 2. So there is always at least 2 and up to, at this point in time, 5. And we have 52 edge locations, and they are used by our CloudFront content distribution network, where content can be cached at those edge locations to reduce latency and to reduce overall costs for us. So what does it look like? So if we have our AWS infrastructure and then we have multiple regions within that infrastructure, and then we also have availability zones within those regions, that's what it would look like, or that's what it does look like. And of course we have many more regions than that, and some regions have way more availability zones than that. So our virtual private cloud is our own little private space within the Amazon infrastructure, and we can have that inside a region and spanning multiple availability zones as I've got there. So before we move on and start talking more about VPC, I just want to make sure that you understand TCP/IP subnet addressing. So if you're an experienced administrator, this will be old hat to you, but if you're not, a lot of your developers will probably, well, may or may not understand this. So a TCP/IP address is a 32-bit binary number that is represented as 4 bytes that are converted to decimal, and I think most of us know that. So we can see the 4 bytes there that make up a 32-bit binary number, and the numbers normally range from 0 to 255. So we also have within the IP range, there are private network ranges. So those are used within your private network. So they're not used for public IP addressing. So if you type it into your browser, it's probably not going to take you anywhere unless it's somewhere local on your local network, and they're not visible to the wider internet. So we have class A, B, and C, and so they A is 10, starts with 10, class B starts with 172.16, or 172, and ranges from 16 to 31, and then we have class C, which is 192, 168. So they are the private network ranges, and they're the network ranges that we would use inside our VPC, or our VPC would use. So a subnet mask. So that subnet mask defines a range of IP addresses. So it defines the IP range of our network. So the ones in that IP mask represent the network portion, and the zeros represents the host. So what does that mean? So that means that we have a network, and then we have those zeros which represent the host. So they're the range of IPs that can be used for hosts within that network. So Amazon reserves the first 4 IP addresses and the last IP address of every subnet for IP networking purposes. So you cannot use the first 4 IPs, so that is, you cannot use 0, 1, 2 or 3, and you can't use the very last one, 255. So just an example here. So if we've got a network IP address, so if our network is 192.168.1.0, and we have a subnet mask of 255.255.255.0. So if we look at that subnet mask, so it basically the first 3 bytes are ones, and then the last bytes are zeros. So that red line there, where the zeros start, is where our network starts. So 192.168.1.0 is our network IP address. And so our first host address is going to be 4, which is 100. So we can't use the first 4. So it's 0, 1, 2, and 3 are not available to us. And then the last is going to be there 254. So our network range of addresses there will be 192.168.1.4 up to 192.168.1.254. And so they're the range of IP addresses within that network based on that subnet mask. So if our subnet mask was 255.255.0.0, then we would have a significantly larger amount of addresses available to us within that network. Okay, so what does that look like? So we've got our network ID there, which is 192.168.1.0, and then we could have instances running from 192.168.1.4 up to 192.168.1.254. So that's what it would look like for that scenario. So then we look at classless interdomain routing or CIDR notation. So that is a shorthand notation that defines a number of subnet mask bits. So the larger the number, the less addresses available for hosts. The smaller the number, or the smaller that subnet mask, the more addresses are available for hosts. So when we look at the example we had for 255.255.255.0, that has 24 ones. Okay, so that is 3 times 8. So that will be /24. Then we have 255.255.0.0, and that will be a /16. And then we have something a little bit more tricky, which is 255.255.240, and that has 20 ones leading it. So that will be a /20 inside a notation. So as an example here, so if we have an IP address range that is 172.31.16.0/20, what does that look like? So the first 20 ones, so we get there the first 20 ones, which will be 16 and 4. So halfway through the third bit is our red line where our network hosts begin. And so our first host is going to be 4 as before, and our last one will be 31.254. So what does that look like? So here, if we had that as our VPC addressing, so we would have our VPC would have 172.31.0.0/16, and inside that we could have subnets, which would be 172.31.0.0/20, 172.31.16.0/20, and then we could have another one, 172.31.32.0/20, and we could keep going on like that until we ran out of numbers there. So that's what that would look like, and how our VPC subnets would look like launched inside of VPC. So the default VPC that comes with, there is a default VPC that comes with every account, provided it's a reasonably new account. And so that default VPC has a CIDR range of 172.31.00/16. But you are free to use other private address ranges. So if you create your own VPC, you can create it with 10.0.0/16 if you would like. So you're free to define your own private address range. Amazon VPC supports VPC ranges between /28, which is very small, up to /16. The minimum size of a subnet is /28 or 14 IP addresses. And subnets cannot be larger, for obvious reasons, cannot be larger than the VPC in which they are created. It just wouldn't make sense if that was the case. If you want to change the size of a VPC, it's not possible after it's been created. So you must terminate your existing VPC and then create a new one. So make sure that you plan out your VPC correctly and making sure that you've got the correct IP address range suitable for your VPC, so that you don't come to the end of your architecture and find that you have to pull it down and recreate it again. So the number of ways of connecting to a VPC. So these are the two ones that you would need to know for an associate level course. There are other ways of connecting to a VPC, but these are the main ways that you would connect and that you would no doubt be having questions on. So the first way is through an internet gateway. And so an internet gateway is a scalable, redundant, and highly available VPC component. What that means is that when you look at an architecture that has an internet gateway or an AWS internet gateway, it's not a single point of failure. So you don't have to create multiple gateways to have redundancy. It has redundancy built into it, so you don't have to worry about that. It provides a target in your VPC route tables for internet routable traffic. And it also performs network address translation from instances that have been assigned a public IP address. So it routes that traffic through to those instances. And the other way of connecting to a VPC is through a virtual private gateway, so a VPN. So that consists of a virtual private gateway, which is the VPN concentrator on the Amazon side of the VPN connection. And it consists of a customer gateway, which is a physical device or software application that is on the customer side of that VPN connection. So one thing to consider here, or one thing to understand, is that the VPN connection is a dual tunnel connection. So what that means is it's a dual tunnel, and it has unique virtual private gateway public IP addresses. So if you want to take advantage of that dual tunnel connection for redundancy, you only need to have a second customer gateway. You don't need a second virtual private gateway to take advantage of that. That is already there. So if you have a question that asks, about increasing the redundancy of your VPN connection, then all you need to do is supply a customer gateway. You don't have to supply anything else to your architecture. The virtual private gateway has a dual tunnel VPN connection through to it. So there are other options there as well. So including AWS Direct Connect, which is a direct connection between an enterprise's premises and AWS's resources. So that's more for very large organizations that would be using AWS Direct Connect, but you need to be aware of that. So route tables, so they are required for an instance to connect to the internet. So an instance needs an internet gateway, it needs a public IP address, and it needs a route. So it needs a custom route table that will be explicitly associated to that subnet that will route traffic from it to the internet gateway. Without that, without any one of those three occurring, or being available, then you will not have access to the wider internet. So if you have a question that says you cannot connect to the internet and you have a route table that doesn't have a route to an internet gateway, then that would be the issue. Or if you're trying to connect the internet and you don't have a public IP address, and that would be an issue as well. So you need to have those three: an internet gateway, a route through to the public subnet, and a public IP address. So a main route table is automatically created when you create a VPC using the VPC wizard. And so that main route table, which is default route table, will just allow local traffic within the VPC. So you can see there our VPC 10.0.0.16, and it's only allowing local traffic there. Now, if there's no route table being explicitly created and associated to a subnet, it will automatically inherit or implicitly be associated to the main route table. So a custom route table is also automatically created when you create a VPC using the VPC wizard, and that is one that allows traffic from your public subnet through to the internet gateway. And so it creates a route to the internet gateway, and it is explicitly associated to your public subnet. So the subnet that you want access to the wider internet. And so that's what it looks like there. It will have the local traffic allowed, but it also will have destination everywhere will go through to the internet gateway. So we talked there about public and private subnets. So our public subnet, which is what we would, if we were looking at, say, a LAMP environment, we would probably have our application and our web server and everything in our public subnet, and that would have a custom route table explicitly associated that would allow traffic, not only local traffic, but traffic through to the internet gateway and out to the wider internet. And our private subnet, which would probably contain our database, because we don't want people to access our database directly, and that will allow just local traffic, which will allow it to communicate with the application server that's located in our public subnet. So there are times when a database inside a private subnet will need to connect to the internet gateway. And those times are when it needs to download updates, for example, or something like that. So to allow it to do that, we have a NAT, or network address translation, to a internet gateway. So we'll allow that traffic to occur. So previously we only had one option for that, and so there is now a new service called the NAT Gateway, which is a fully managed service by Amazon Web Service that allows traffic to flow from a private subnet to an internet gateway for to download updates and the like. And so the VPC main route table, which is implicitly associated to the private subnet, will need to be updated to have a route for everything to go through to the NAT gateway. We can also use a NAT instance, so we don't have to use the NAT gateway, we can use a NAT instance. And in the tutorial, or in the lab on highly available architecture, we use a NAT instance there to allow our RDS Aurora instance to download updates through from the wider internet. So again, you would have a main route table entry there that would have all other traffic going out to the wider internet would be routed through to the elastic network interface of that NAT instance. So VPC security, so we have obviously we have our route tables and we have all this sort of thing going on, but we also have other layers of security. So we have our security groups, we have our network access control list, and we have our flow logs. Our security groups, they operate at the instance level, and so they are associated to individual instances or individual EC2 instances that are launched within our VPC. Whereas network access control lists they are associated to subnets. They're not associated to instances, they're associated to subnets. So they provide an extra layer defense. So if you relaunch an instance into a subnet and doesn't have a very good security group, the network access control list will provide a second layer of security for that. So it will it will control that instance that is launched within that, even if it does have a poor security group. And a new service is flow logs that are available. So they capture information as CloudWatch logs on traffic that is flowing in and out of our VPC. So it's very good to diagnose problems with our VPC architecture. So flow logs is another good security tool in that toolkit. So the differences between, I'll just quickly run through the differences between security groups and network access control lists. So a lot of this may not be completely sinking in, but rest assured when you do the lab that's coming up after this lesson, it will become much clearer to you when you get your hands on and build a VPC and start building these subnets and whatever and security groups. It will become more apparent to you how it all works. So just a quick overview, and we will recap this on the next lesson as well. A security group, and again, it operates at the instance level. It's the first layer of defense for us, and it supports only allow rules. So there's nothing there. It's basically a deny, and we need to put in allow rules to allow things to happen. It's stateful. So what that means is that return traffic is automatically allowed. Regardless of any rules, return traffic always goes through. We evaluate all the rules before deciding whether to allow traffic. So if there is, so what it will do, it will go through, evaluate all those rules, and then it will make a decision to allow that traffic. So if there is more than one rule for a specific port, it will apply the most permissive rule. So this needs to be clear. So we're talking about the most permissive, not the most restrictive. So if something has, because we're supporting allow rules, so if something allowing a lot, that will prevail over something that allows a little. So it is the most permissive, not the most restrictive rule. So it applies to an instance only if someone specifies that security group when they're launching their instance, or they associate it, that security group, to the instance later on after it's been running. So network ACLs, so they operate at the subnet level and they provide that second layer of defense. So if you have a poor security group, that instance will still be controlled at the subnet level by a network access control list if it's there. It supports both allow and deny rules, and it's stateless. So return traffic must be explicitly allowed by the rules, otherwise it will not happen. So we process rules in number order, and when deciding whether to allow traffic, the most restrictive denies. So that's the opposite to a security group where the most permissive applies. The most restrictive deny applies. So it automatically applies to all instances that are launched within that subnet. And it's a backup layer of defense, so you don't have to rely upon someone specifying a security group, but you should always use security groups, have good security groups at the instance level, and have network access control lists at the subnet level. So that's a very quick overview and very theoretical view of VPC. So coming up now is some very, very complex and very interesting hands-on lab on creating a highly available architecture inside of VPC. So have fun with that.